really appreciate you being here, on a Friday this evening almost, for a very dry topic. I'll try to make it very interesting as much as I can. So let's do this. We'll kind of do the introductions at the end. We'll get into the topic, and the way I'll do this is we'll kind of pursue a very simple example that we can actually go through end to end, right here, right now, to actually understand the intuition behind the genre of solutions that I'm about to talk about. Right? So, what really triggered this to begin with, right? So, like, necessity is the kind of mother of all innovation. Same for us, we are a scale-up, desperately trying to get cash positive, and one of the biggest nemesis that we had, as we started selling to more and more customers is the cost of data processing, right? And if you're a data engineer leader in any organization which is handling the plethora of data, you know the pain, right? So once you've handled scale and speed, cost becomes your biggest problem. So let's explore today a very simple use case where I'll show you how you can actually achieve the same things that we do on day-to-day life, in analytics space, in data engineering, using a different genre of applications, or solutions. So the problem is very simple, right? So it's as simple as, let's say, you're counting the number of impressions your users have seen, right? So you have advertisements that are running on two types of domains, web and mobile, and all you're doing is just tabulating the counts, right, in a particular month of viewers. So let's quickly do a math of what is the worst case storage that you need to handle this. So let's say you have 1 million users, and per user you have a 64-bit hash. So if you're wondering what this might be, it could be like a hash of an email ID, some other identifier, whatever be it, right? So you're basically maintaining some kind of a key that by which you can recognize a particular user, right? And remember, we chose like 2 dimensions only, right? Like for a particular dimension, like a cardinality of 2, web and mobile. So what you end up with is 64-bit, which is 8 bytes of data, times 2, times your 1 million your number of users. You basically get 16 MB of data per advertisement, right? Again, worst case storage estimate. So if you have like 100,000 ads per day, this goes up to 1.6 TB of data per day. For a month, multiply with 30, near about 50 terabytes of data per month. Worst case storage estimate, right? In actual, you will have at least a few terabytes of data. In actual, you will have a lot more dimensions than web and mobile, right? The device type, you could have n number of demographics, age, gender, salary levels, blah blah blah. Like today, like in Zeotap, we have like almost 300 dimensions, by the way, just to give you a glimpse. But anyways, we came down to 50 terabytes. Actual, probably a few terabytes of data, right? The problem. Now the problem is that, let's say you have done this for a particular month. You're gonna do this month on month, and that data just piles up. Why does it pile up? You're gonna do analysis across months, right? Like let's say you are trying to figure out, okay, number of users that had viewership of a particular advertisement in August, how does that overlap with people in January? What are the demographics of it, so on and so forth. So you'll actually have to hold on to that data month on month for at least a period of or window of time that actually entails your analysis, right? It could be at least a year or whatever. So your data just piles up. Every time you do this compute, you have to go back to the raw data. Why? Because additively, you cannot figure out, like to give you an example, let's say you have done the computation for a particular month, you cannot just, progressively add, like update your results based on new data that is coming in, right? That's one big problem. And this is just one type of use case or aggregation that I'm talking about, which is just the, distinct count of users. You could have n number of different kinds of aggregations that you do, like you could have overlaps, like I said, month-to-month analysis, quarter-to-quarter analysis, year-to-year analysis, and so on. You could try to find overlaps where you are finding common users between two particular months, 2 particular quarters, and so on. You could be computing quantiles, you could be finding the most frequent genre of users or group of users for a type of advertisement and so on. Graph analysis where, let's say you have, this is very atypical to ad tech, where you're running advertisements on cohorts of users and you have an ID graph, right? So you're trying to find out what is the overlap between that cohort with your ID graph and what are their nearest neighbors, which is basically, additional people you could target for your advertisements and so on, right? So if you notice all of these use cases, like all of these aggregations that you're doing, right? Every time you have to do it, you have to go back to your raw data because you just cannot additively or marginally, update your results based on new information, right? And that poses the biggest challenge because now your data just piles up for whatever period of time that you need to, use data for your analysis. You have to just hold on to that data. Every time you compute, you have to go back to your raw data, right? So your compute cost keeps going up. Your storage cost keeps going up. Why does it keep going up? Because year on year you're going to have data growth, right? As simple as that. So that's the genre of problem, right? Now, implicitly, there is an assumption that we have made while we have concocted all these solutions. And that assumption, if we could do without actually, could kind of open up the gates for a very new type of solution that can minimize cost, bring down compute cost, like not just storage cost, your compute cost as well. Speed up your analysis. You can do real-time analytics, real-time dashboarding, all of that at kind of like minuscule cost, as compared to the genre of solutions that we are more familiar with. And that assumption is essentially the fact that that we have to be exact with our numbers. Now, if you think of it, like there are a lot of operational use cases where numbers have to be exact, but decision-making systems, a lot of even operational use cases like fraud analytics, signal anomaly detection, and so on, they are hell-bent on scale and speed rather than accuracy because you need to generate your alerts at real time to be able to detect an anomaly or a fraud, and then it goes through a process where it could be manual intervention, it could be additional automated checks and so on. But you don't really need exact numbers to begin with. And then reporting, if you think of it like dashboarding, which facilitates any kind of decision-making process within organizations, right? That definitely doesn't need accurate numbers. So if you could do away with that, like exact accurate numbers, you could actually explore a genre of solution, which is what I'm about to talk about. So let's get into it. What I'm about to do is I'm going to present you a specific solution, which many of you might have already heard about and you will be familiar with it. I'm going to go into the depths of it so I can kind of show you the intuition behind it. All right. So this is the count-min sketch. It's a data structure. It's a probabilistic data structure. Sketch is the most frequently used term you will hear about. A very famous sketch that you will definitely have heard about is Bloom filters. Most of you might have used it already. It's another sketch, a probabilistic data structure. So let's get into this fast. I'll first explain to you how it actually works, just the algorithm part of it, and then I'll tell you why it even works to begin with. All you're doing is you've taken a D by W matrix, all right? Each slot is essentially, you're storing an integer into it, right? The counts. How are we updating it? For input I, you are, now if you're wondering where did we come with that input I as an integer, right? So we talk about the hash, right? You can convert a hex hash into an integer number and then carry on with it. So there are a number of ways of doing it, right? So let's just go on. So for an input I, what you're doing is essentially you have a hashing function which maps, like there are not one hashing function but de-hashing functions for each row, and you're mapping to a slot within a row, right? How are you doing it? So how do we come up with a hashing function to begin with, right? So let's say if our total count, like the entire universe of impressions in our case, right, was n, whatever be that number n, then we just need to find a prime number t which is like greater than n. And the reason for finding that is this two coefficients aj and bj that you see, you're basically selecting them randomly between 1 and t minus 1. Okay? This is just one very simplistic choice of hashing function. Actual implementation of sketches are much more optimal. They use many sophisticated hashing functions, but I'm just giving you a very simple example. This works for us. So what it does is, if you notice, you compute that aj times I plus bj, and then you do a modulus of p, then a modulus of w, which maps to a w bit stream, right? So for each input, for each row, you've mapped it, right? This C is basically a counter. Like if you had a 1 as a counter, you just keep adding it, right? Once you've added all that, when you want to find the actual number of impressions for this guy I, all you have to do is recompute the hashes to find their slots, and then take the minimum of it, okay? That's what a count-min sketch, how a count-min sketch works. Now, question is, how does it even work? Why does this even work, right? How do you even quantify the amount of error you're going to have in the estimate? So let's look at it. Don't worry, this is very simple. So most probabilistic data structures, actually what they do is, like we have studied about different probability distributions, right, in our school days, college days, whatever be it. Essentially, what they're trying to do is transform your raw data onto a known distribution. And then, once you've done that mapping, there are already existing known error rates that you can compute on that distribution. Okay, so most of the questions that you're answering of the actual data end up becoming estimates of different parameters within the distribution, and that is what we're about to look at. So in this case, it's very simple. There is something called Markov's inequality. You might not remember it, you might have read about it at some point. All it does is very simple. In any distribution x, right, for a given positive integer a, or a positive value a, not an integer necessarily, the probability that your x is greater than or equal to a is actually less than or equal to the average value divided by a, okay? Now see the magic that happens. So let's say, now think about it, what we were doing, right? We were taking that total count n, whatever be that count, right? And each hashing function in its own row is just mapping to one of the slots. How many slots? W slots. So what's your average going to look like? N divided by W, right? But then there's no guarantee that, the value that pops up in a particular slot is going to be like exactly the average. It will be more than the average, less than the average, whatever be it. We don't know. But we know that the total average, if we just summed it up, it would be, the sum would be n, right? So the average is n divided by W. Now all we are doing is, the choice of A we made is like twice the average. Don't worry about it, why we did it. We did it empirically, you'll see why we did it in a bit. So we chose A to be 2n by W, okay? Twice the average weight that it should be. And our average, the expectation of x is obviously n by W, as you know. So you replace it into that equation, you basically get this. So what this says is, the probability that a particular slot is greater than or equal to the twice the average is actually less than 50%, okay? Why is this interesting? Now, remember that these were independent hashing functions, right? And because they're independent, when you take the joint probability, you'll end up having a nice multiplication because they are all independent. So, remember, independent events, probability of them, you can multiply the probability of those events separately, right? So that is what we did. We just multiplied all of them for all the j, which is the d number of hashings that you did, right? You got this. So it's less than or equal to half to the power t. Now we did the flip, which is the contra of this event, right? So xj is less than or equal to 2n by w is greater than or equal to 1 minus half to the power t. Don't worry about the structure. Just look at the equation, and what you're seeing is, you just quantified what amount of weight goes into a particular slot, right? It will always, with what probability will it be less than or equal to 2n by w? The probability will be at least 1 minus half to the power t, right? Okay. How do we use it? Now let's come to actual, like what we really want to do. What we want to do is we want to quantify our error, right? The error should be within a particular limit with a certainty, right? So if we say that the max amount of error that we want to allow is 0.1%, okay, 0.1% of the total count n with a sanctity of 99.9%, then what you end up doing is 0.1% of n is equal to 2n by w, right? Which gives you a w value of 2000. And that 1 minus half to the power d is greater than or equal to 99.9%, gives you a d value of greater than or equal to 9.97, so you choose a d value of 10. So what you got is a 10 by 2000 matrix, which assures you a 0.1% error with a 99.9% confidence. How cool is that? And if you do the maths, each slot is basically a 32-bit integer, in our case, 4 bytes. So 4 times 10 times 2000 is 80 KB. So we came down from a few terabytes to 80 kilobytes. The magic actually just starts now. On top of that, if you think of it, so basically what you did end up doing, right? You computed this for a particular month, right? Same as our raw data. So raw data we mapped onto this. Every month you could have a different sketch. If you wanted to accumulate data or look at the aggregates across a particular window of time, you just have to add those matrices, as simple as that, which you couldn't do on the raw data. You had to go back and recompute. So that is another magic that sketches bring, which is composability. It allows you to compose data across multiple sketches, multiple periods of time. You never have to go back to your raw data. You can update the sketch based on additional inputs. And that's the whole genesis behind this genre of solution, using probabilistic data structures. What they essentially do is take your raw data, transform into some kind of a known distribution, as I was saying, and then the actual answers that you need, right, the questions that you're trying to answer are basically point estimates of that distribution. Okay? What do you get out of it? Definitely way below sublinear query space. The transformations, like the sketches now are additive, so you are able to do whatever you want. Like composability allows you to like aggregate across sketches without ever going back to raw data. In near real-time processing, stream processing, and so on, right? You are able to, you can create these sketches on a distributed manner on different silos of data, and then aggregate them, as you wish, as you need. Okay. So pretty much, it gives you scale, speed, and cost. Obviously, will improve both from storage as well as compute. This example I chose so that we can go over it in very less time. But there are a plethora of these sketch algorithms actually, which are tuned towards different types of problems. Okay, so we started off with a distinct counting problem, right? Basically, any kind of summations that we do fall into that genre. And there are many types of sketches within it. Like there are the CPC sketches, then there are HLS, theta sketches, tuple sketches. CPC primarily where it helps is in terms of streaming data inputs. It allows you scaled updation of sketch, because again, there's no magic, right? So even with this level of optimization, if your data starts going beyond petabytes, even with sketches you will start running into problems. So imagine you have real-time use cases where users are waiting for certain inputs on an interface, right? And your data is like in terabytes at a streaming level. Even with sketches, you'll have to optimize in that case, right? Which is why you will see different types of sketches within a particular genre of problem itself, which actually each sketch optimizes a certain side of it. Like some optimizes storage, some optimizes on update speeds, some optimizes on compute needed to actually query it, and so on. Right? So CPC, hyperlog are two genres. Theta sketches in particular, I'll just tell you so that you can explore later, allows you to perform set operations, like intersections and unions, which become very critical because when you analyze data across different periods of time and you don't have access to the raw data anymore, right? Like you have to find overlap counts and so on, right? Theta sketches will give you that with a very high amount of, very low amount of error. Tuple sketches allow you to perform approximate joins. So think about it, when you do your analytics, we often join big data sets together to actually get maybe additional dimensions, maybe overlap of the actual metric that you're computing and so on, right? So tuple sketches allow you to do that actually. You don't need to do a join on raw data anymore. You can have your sketches of data sets separately prepared and you perform a join or an overlap on the sketch itself to get the numbers out of it. Okay? Another type of problem is most frequent numbers, then quantiles. Quantiles is a big pain because once you compute a quantile, there is no way on earth using raw data you can marginally, update the results, right? You have to go back to the raw data to do it. Sampling. So there are various sampling methods, based on statistical methods, right? This basically kind of allows you to, so reservoir sampling as well as thereof sampling, what they allow you to do is on streaming data to provide sampling on top of it because you haven't seen the entire set of data, right? So how do you really provide a sample of a stream where you don't even know what the entire population looks like? This is what it does, right? So very interesting, problem statements that you can actually explore in your time. Just within the count sketches itself, there are so many varieties like we talked about. Like I said, set operations are not necessarily done by everyone, right? So there are various parameters by which these different types of sketches actually different kind of sketches actually try to optimize, like I said, right? So don't worry about it. In one of the slides, I have the URLs that you can actually take away. So you can actually access the documentation that you need to look at to actually learn more about them. Implementation, when it comes to implementation, obviously this is no, very simple thing to do, right? So a lot of these statistical methods that or the distributions that you need to implement require specialized algorithms. And we are in luck because Apache has an entire library dedicated towards it, Apache Data Sketches. This QR code will lead you to the documentation link, so you can take it. So this library essentially provides you base implementations of most of the well-known sketches or the genres of problems that we already saw. All right. One of the things that I didn't mention in the last slide is I don't know if you noticed, once you're done with this QR code, I'll go back to the last slide. So most of the library actually implements on top of primitives, but let's say in your actual data, you will have different types of complex structures, right? Or object structures on which you might need to perform sketches. So you will probably have to write some wrappers on top of this. But like I said, they are already providing the support on primitives, so it's not a big deal to write wrappers. That's just one of them. So in the last slide, if you notice, there are the input types that they already support. This is from their documentation library. Another thing is the language is supported. So they provide Java, C++, as well as Python support. So Java library can be used both in Java and Scala, C++ and Python. All right, let's move on. So yeah, now, like I stated earlier, we looked at data sketches out of compulsion because we had reached a certain volume where we just couldn't operate anymore, living within the boundaries of the cost that we had to live in as a startup organization. We don't have infinite money. But then we used it pretty much across our reporting applications, right? Where we don't need exact numbers. Customer insights is one which is like a, if you imagine a dashboard of sorts, which is providing demographics on tops of cohorts of users, right? Like you have a cohort of users as input, and you're basically letting the user know the distribution of those users across different types of demographics, right? Entirety of it was done using sketches. Graph match is what we have done. Like I was explaining earlier, you want to find the overlap with the graph, and then you want to find their neighbors, and you want the count of those neighbors, right? Even that we did using sketches. A very quick brief about Zeotap. So we started off as a data company. We used to be in the data business line where we were monetizing data to begin with, and in the last few years we have pivoted towards customer data platform. In a nutshell, what it does is, I'll give you an example. So let's say think about a retailer like Amazon, right? So Amazon has so many customers, right? And they want to run campaigns for those customers, right? So what we essentially do is we provide that pipeline of sorts where they can bring in their customer information into our platform, the customer data platform, and then do various transformations on top of it, or let's say run different logic on top of it to create segments or cohorts of customers, and then push those cohorts onto different ad tech platforms for activation. Like, let's say when you go into Facebook and you think, okay, I just did a Google search of laptops, and so intelligently Facebook is showing me laptop advertisements. We enable that. That's precisely what it does. Okay, and that's about it.